Hi, this is Ojas Parekh, and I want to tell you about approximating quantum generalizations of Max-2 CSP. This is joint work with Sean Hallgren and Yun Lee. So let's just begin with Max Cut and some relaxations for it, and then we'll talk about vector generalizations of Max Cut. So here we've got the standard formulation for Max Cut in plus or minus 1 variables, and here's the standard relaxation. We can get a generalization of Max Cut by considering the relaxation, and instead of having vectors that live in unspecified dimensional space, we can fix the size of the space that they live in. And of course, if we insist our vectors live in R1, we recover Max Cut, but we could say they live in R2 or 3 or some other constant value. In this case, we get rank constrained Max Cut, which was first considered by Briette et al. And specifically for the 3-dimensional case, they get a 0.956 approximation. These factors get better as the dimension of the space increases. And here we're looking at 3 because 3 is kind of a natural setting for problems arising in quantum information. In particular, recently with Sev Garivian, we looked at a quantum generalization of Max Cut. And for that problem, every feasible solution to this problem is feasible, but there are additional, more quantum solutions that aren't feasible. And so we get a 0.498 approximation with respect to the class of solutions that happen to be feasible for this problem. These are called product state solutions, and they're actually, you can think of them as classical solutions to quantum problems. When we talk more about these problems, we can talk about just approximating these kinds of classical problems as is, or we can compare them against sort of the optimum value of the more general quantum problem we're interested in. We can, in fact, generalize this even more and now introduce, instead of taking an inner product here, we can introduce a matrix in between these vectors. So this introduces some difficulties in rounding and approximating because we're no longer allowed to relax these vectors to live in a higher dimensional space. We have to be a little more careful about how we do that because this 3 by 3A matrix is sort of given as input. One thing we can do is take each entry of these vectors and relax the scalars to vector values themselves. And this is the kind of approach we take for these approximation algorithms. So for 2 CSP, things are slightly more general. In the classical case, we have now linear terms. Most closely related to the problem we consider is this generalized rank 3 Max-2 CSP problem, where now, as before, we imagine we have 3-dimensional vectors kind of living on each vertex or for each kind of, in place of each Boolean variable. And the objective is determined, by 2 given vectors and a matrix. So these are linear parts, the quadratic part, and then everything else is kind of as the same. And what we do specifically is we look at instances of this problem where the A's and B's, they come from a quantum generalization of Max-2 CSP. So before we get into quantum generalizations of these problems, let me tell you a bit about qubits. So in the deterministic setting, we, of course, if we have Boolean variables, they take 2 values, heads or tails. In the probabilistic setting, we can imagine assigning a real value to each variable. And in the quantum setting, which is even more general, it's kind of like the probabilistic setting in that we have a state, and the state has information that we can't directly access, but what we can do is measure it. So the idea is that these are called kets, so 0 ket, and 1 ket, these 2 kets, think of them as basis vectors for 2-dimensional complex space. So 0, this 0 ket might be the vector 1, 0, and the 1 might be 0, 1. And these alpha and beta here are complex coefficients. So this is a 2-dimensional vector. So there are 2 complex values that are kind of used to indicate the information in this qubit. But what we're allowed to do to access this information is just kind of perform a measurement, which lets us see this value 0 with probability, the absolute value of alpha squared, and we see 1 with the probability absolute value of beta squared. And so, just like in the probabilistic setting, we have a probability of seeing 0 or 1. However, there's extra information that's carried through the computation and allows us to produce or sample from probability distributions that have nice properties. And this is kind of the basis of taking advantage of quantum information, to do computation. So as mentioned, we have 2 complex values here, but there is a normalization constraint because these have to act like probabilities. And so we can actually think of this qubit as being parameterized by a 3-dimensional sphere. The 3 real parameters are kind of enough to specify the information here. So to actually do computation with these objects, we can think of a conceptual model that's pretty simple and will get us everything we need for this talk. What happens is that we perform some physical manipulations on these objects, and then we have the joint state of these n things at the end of the computation or physical manipulation. But conceptually, what's going on is that we're starting with a probability distribution over all the possible states, the output states of these n qubits. Again, when we measure, we only see zeros and ones, so we only have 2 to the n probabilities of kind of seeing one of the basis states here. And when we kind of perform these operations, as mentioned, they're unitaries, so we will in fact end up with a unit vector at the end, and we can measure in the computational, the standard basis to get a single string out, a single classical string with some probability that's kind of dictated by this unit vector. And so that's the idea. We want to take kind of a sort of initial state, initial probability distribution, usually with everything concentrated on the all zero string, perform our quantum operations. There's an issue of kind of these gates have to be efficient, so they usually only operate on 2 qubits at a time. However, at the end, we want to produce a distribution, at least for optimization, where the probability of seeing good things, good feasible solutions is high. And so this is the idea. When I say quantum state, I really just mean a unit vector in a 2 to the n dimensional complex space. So one very nice thing that actually, I was very excited to hear about when I first learned it, and I was kind of oblivious to, is that there's a very natural link between kind of how nature works and discrete optimization. So, it turns out that physical systems have energy levels, and you can represent this in what physicists call Hamiltonians, which is really just think of it as an exponentially large matrix whose eigenvalues correspond to the different energy levels of a physical system. And the reason that they're eigenvalues is that this Hamiltonian kind of dictates how a physical state evolves. We apply the Hamiltonian to a state in some sense to kind of update it or to evolve it. And of course, if your state, when you apply the Hamiltonian, is preserved, this is in some sense kind of a stable state. It's an eigenstate. And so these are the ones that actually we care about, and the energies of the associated states are encoded in this Hamiltonian. And so for various reasons, one thing that people would like to understand is low energy states of physical systems, because nature is sort of inherently trying to put physical systems in low energy states. It's not always succeeding, it's a heuristic. So let me give you an example. Let's say we wanted to represent kind of the max cut problem as a Hamiltonian. So one thing we could do is we could just look at a graph here. I have a path on 3 vertices, and we could write down the various objective function values for each configuration of the vertices. So here, I've used quantum notation, but the idea is that these are binary values just telling you on which side each vertex lives. So this, for example, is the cut where vertex 3 is on the right and vertices 1 and 2 are on the left. And this is the associated value, which is 1. The reason I've negated them is because we typically think about finding low energy states, so we want to minimize. And so for max cut, of course, we'd have to negate the objective. And here, just to further drive home this point, I've given a few examples. So for every possible cut of our graph, we've kind of listed the objective value. And so by construction, the eigenvalues here, it's a diagonal matrix. The eigenvalues are simply listed on the diagonal. They correspond to kind of different configurations, and the corresponding eigenvalues are just the basis vectors, which correspond to a cut. For now, I want to explain how we actually get problems that aren't just classical optimization problems in this framework. So before doing that, I just want to talk a little bit about quantum computing. The power of quantum computing, like most other things in complexity theory, isn't really well understood. And the class that people typically think of as efficient quantum computing is called BQP. The B here is for bounded error probability. It's a probabilistic class. And so, the natural analog would be something like BPP. So BQP, we don't expect to be able to solve NP-hard problems using polynomial time quantum computation. However, we do expect to be able to do things that are outside of P. So again, the problem we're solving on quantum computers is a sampling problem, and so it's not quite a decision problem. And so we might be able to, in principle, solve different kinds of things. And in fact, there are complexity results that say that kind of efficient low-depth quantum circuits can generate states that if we could sample from classically, exactly or even approximately in some sense, then the polynomial hierarchy would collapse to the 3rd level. And so we already know that there are likely to be kind of sampling problems that you could do on quantum computers that you can't do classically. But here we're talking about optimization, so things are a little different. I want to mention that using kind of nature, and its tendency to kind of put systems in their low energy states to solve optimization is an old one. You may have heard of using soap film, soap film computing, if you will, to find Steiner trees. And it's a heuristic, it doesn't scale very well. It performs as well as you'd probably think. But these ideas have been around for a while. What's different about quantum computing, and actually quite interesting, is that this idea of kind of optimizing in Hamiltonian is closely related to a model of computing called adiabatic quantum computing. And up to polynomial factors, that's a universal model. You may have heard of things like the quantum approximate optimization algorithm, which is kind of a discretized version of adiabatic quantum computing. So there's some very natural ways to tackle optimization problems quantumly. However, coming up with rigorous guarantees is harder. So back to these Hamiltonians being exponential size, the way we deal with this is the same way that we would deal with this classically. If you're giving me a classical CSP, it's really a function on n variables, but I'm only giving you a clause at a time. So the idea is that we do the same thing. I tell you kind of what's going on 2 of my qubits, and then I tensor with identity on the rest to get an exponential size matrix that really only kind of has constant information within it. And then I can sum these together to get a representation, of my Hamiltonian. And the key here is that in quantum computing implementations, this is not something you do explicitly. Tensoring with identity means that you're basically leaving the rest of the system, kind of intact, and are only manipulating kind of 2 qubits at a time. So this is kind of shorthand for just saying that we're operating only on a subset of, or a subsystem, of our larger system. Next, let's talk about quantum generalizations of Max Cut and other CSPs. So as suggested on previous slides, if we kind of look at diagonal Hamiltonians, we get classical problems. And the way to think about this is here, I've got a CSP Max Cut on 2 variables. And if I look at the diagonal here, that's encoding the value of the CSP itself. So on 0, 0, we earn nothing. On 0, 1, or 1, 0, we earn 1. And on 1, 1, we earn nothing. So the diagonal here encodes some Boolean function. And if we wanted to, we could also express this Boolean function as a polynomial in plus minus 1 variables. And we can go back and forth between the function as specified on the diagonal, its values, and as a polynomial by doing a Fourier transform. So in the quantum case, the idea is that now, how about if I don't look at diagonal Hamiltonians? So for each clause, I can just have an arbitrary 2x2 matrix that's kind of telling me, sort of the inherent eigenvalue optimization problem I want to solve on those 2 variables. And the key here is, of course, that now optimal eigenvectors may not be compact. They may not just be a classical basis state or a single string. They may actually be a vector that's a linear combination of many of these. And on the full Hamiltonian, you may have exponential size solutions. That right away is a problem if we're trying to solve these things classically. However, as noted, ultimately the problem we're solving is a sampling problem. So maybe we don't explicitly have to kind of give a state. We just have to be able to sample from it. In this case, the maximum solution has energy 1. However, if we're only thinking about basis states or as mentioned previously, classical product states, the best you can do is a half. So here's a problem. Here's an instance where the gap between the best quantum and the best classical is already a half. So we could also think about 2CSP. So if we want to figure out how to generalize 2CSP to a quantum setting, we think about kind of a defining characteristic. And of course, a defining characteristic for, let's say, max and, which is kind of equivalent to 2CSP. I have clauses which are disjunctions of 2 variables, max 2 and, I should say, is that there's only one satisfying value for each clause. And so another way to think about that is that this matrix is a rank 1 projector. And so we could, in the quantum case, we could say, hey, now I want just any matrix, not necessarily a diagonal one, that's a rank 1 projector. And this is what gives rise to quantum 2CSP. I should mention that random assignment also makes sense in the quantum case. And there it corresponds to just kind of picking everything on the diagonal with kind of equal probability, so that the entries on the diagonal sum to 1. And so if you have a rank k projector, you get k over 4. And so that gives us a 4th approximation, both classically and quantumly. And so this is really what we're trying to beat. Only recently have there been quantum approximation algorithms beating random assignment. So to put the work in perspective, again, the max 2-local Hamiltonian problem is just that we have clauses on 2 qubits, and we tensor with identity to kind of get the full Hamiltonian. So the point of this slide really is to show you kind of what work has happened, and really, you know, the style of work that leverages SDP relaxations and generalizes classical rounding schemes is very recent, only the last few years. That's in this table. And so these problems are all QMA hard, and QMA is sort of the quantum analog of NP, you know, of probabilistic NP, of MA actually. So, so you know, these problems are hard even for efficient quantum computers. But what we're doing is we're finding approximations in P. So the theme here is finding P approximations for QMA hard problems. And local Hamiltonian in some sense is like the SAT of quantum. You know, it's kind of a problem that's routinely used to show kind of completeness and hardness results. So the nice thing here is that these quantum Hamiltonians often have natural kind of classical CSP specializations. So we know, you know, what we ought to use to kind of generalize and compare against. So one of the early results was for traceless Hamiltonians. You know, you can think of this as kind of classical CSPs where we don't have constant terms. So these, in fact, are harder to approximate, and the best classical results, you know, this is also just kind of quadratic programming with plus or minus 1 variables. You get a log approximation, and then Bravi et al. Gave a log approximation for this. For the problem we consider, which is max positive 2-local Hamiltonian, here, the only constraint is that each Hij, you know, each kind of 4x4 matrix has to be positive, and let's say it has to have eigenvalues between 0 and 1, you know, where like a 1 is satisfying it completely and a 0 is not satisfying it. So the natural analog is MAX-2 CSP. Classically, there's a 0.874 approximation. However, on the quantum side, we've only recently beat random assignment, and in this talk, we'll give the best result known so far. I should mention that this notion of using product states, you know, to compare against quantum opt has its limitations, and as noted earlier, you can come up with examples that give gaps. So here, the best we could possibly do is a half if we insist on using product states. Now, a special case of this, that quantum generalization of Max Cut, is called the Max-Heisenberg problem. And there, of course, you know, we have the Gomez-Williamson approximation. And there, recently as mentioned, there's a 0.498 approximation where 0.5 is the best possible. So that's pretty close. What's really interesting is that recently, Anshu et al. Gave an approximation that beat this 0.5, but they actually round to proper quantum states. You know, it's a classical approximation algorithm, but they are still able to produce a description of a quantum state as output. So this is really where we'd want to go. You know, this is kind of the goal, but it's sort of difficult to do, and we're kind of learning how to do it. So to put this in perspective, I want to talk about polynomials and quantum optimization. So as mentioned before, we can look at these matrices, these poly matrices, Z, X, and Y, and we can use them as a basis for all Hermitian matrices. And so this notation here, Z2, think of it as kind of corresponding to a classical variable on vertex or qubit 2. Formally, what it is it's the tensor product of a bunch of identities and the Z matrix in kind of the second spot, you know, corresponding to the second qubit. We can also do higher order kind of products here where we, you know, for example, Z1 times Z3 is just going to be Z1, which would have a Z on the first spot, identities everywhere else, times Z3, which has a Z in the third spot and identities everywhere else. So this is how we construct polynomials. We take we construct matrices and polynomials. You know, we take tensor products of these operators and they square to identity. So in fact, we only need to look at multilinear polynomials in these variables. And the thing I want to mention is that if we only restrict ourselves to the Z and identity, so if we only look at polynomials using these matrices that you get with identity and Z, this in some sense is completely equivalent to the classical case. You know, you can replace the Z's with plus minus 1 variables and everything works the way you would expect. However, if we include X's and Y's, then we get truly quantum stuff where we'll get off diagonal entries. And so, you know, in general, we'll get a Hermitian matrix here using polynomials like this. So what's a solution to a problem here, to one of these optimization problems? Well, what we want is we want to produce a matrix that's positive with trace 1. And so in the classical sense, you know, this is just a probability distribution. We want a probability distribution over classical solutions, and we can write a polynomial for it here. You know, again, as mentioned, we can go between this vector and this representation using a Fourier transform. And in the quantum case, we want something similar. We want the same thing, actually. You know, it's similar because what this means is slightly different, but the actual conditions are the same, is that we want the matrix to be positive in trace 1. And so now it's a convex combination of rank 1 matrices, which in quantum are called pure states. And so this example corresponds to the polynomial I minus x1, x2, minus y1, y2, minus z1, z2. And I'll keep using this example. So the optimization problem we actually want to solve is we have some Hamiltonian that we're writing as such a polynomial. And then we have a solution that, as mentioned, is PSD in trace 1. And then the goal is to just maximize the trace of H and P. You know, it's a trace of two matrices. These are both Hermitian, so it's really like the entry-wise, you know, inner product of these two matrices if you vectorize them. So in this example, you know, H is I minus Z1, Z2, which is really just these two strings here. It's max cut again. And an optimal solution, for example, is this polynomial where you're just picking 0, 1. In the quantum case, it turns out for this particular example that itself is an optimum solution. This is a rank 1 matrix. Its trace is 1, and so it optimizes itself, you know, and gives you an energy of 1. In general, what we want for a quantum solution is a polynomial, as mentioned, PSD in trace 1. However, classically, you know, these things could be exponentially large, so we need to restrict the space to be able to come up with classical approximations. And the way to do this is to consider what are called product states. Product states are very much like, you know, drawing independently from a bunch of random coin flips. These are sort of kind of probability distributions where what's going on in each qubit is completely independent of everyone else. And so there's no kind of quantum correlation between the different qubits. So as a polynomial, this is expressed as the product of a bunch of terms that are of the form I plus alpha xi plus beta I yi and gamma I zi, where the alpha, beta, and gamma are real scalars, and the sum of the squares has to be 1. And in particular, you know, if we made alpha and beta, let's say 0, and we only had gamma to be plus or minus 1, this would correspond exactly to a classical kind of solution where we're producing, you know, an exact binary string as output. So here, just to kind of drive home an example, you know, as mentioned before, we can look at a quantum polynomial. The best product state solution is just picking this. It gives you an energy of 1/2. And then random assignment it turns out corresponds to the solution where we put, you know, uniform kind of vector on the diagonal. And so the random assignment on this case earns us a 1/4, as previously mentioned. So now we need you know, we have a way of expressing kind of quantum optimization problems in terms of these polynomials. We need a relaxation. So what we can do is we can generalize the Lasserre hierarchy. So the idea here is that we're looking at a matrix where each entry is some moment of this quantum state. Now what we do is we kind of, to get these moments, we look at various strings on the poly operators, and we sandwich them in between the vector. And this is kind of how you populate such a matrix. You know, so to get an entry, you look at the string on the left, the string for the row, the string for the column, you multiply those to get a string, and that's the moment that you take. So classically, we would just have z's, and we would have some string of z's, and that corresponds to a subset of variables, and that's exactly the Lasserre hierarchy. So this is a strict generalization of that, but now, you know, you have strings over x, y's, and z's for each qubit instead of just z's, and identity, of course, too. So for us, this is going to be positive semi-definite because of the way in which this was constructed. It's going to be a complex matrix. This is the relaxation we'll use. We'll only use linear operators here. You know, this is the level 1 relaxation. And to get, you know, to further relax this, we'll only look at the real part of this. So the final relaxation we look at is the real part of the previously mentioned a moment matrix. And it has a very nice structure. You just have 3 by 3 identity blocks in the diagonal, and it has to be PSD, and that's it. That's the full relaxation. The way we interpret this, you know, of course, when we wanted to do rounding as a vector program, is now we have an x vector, a y vector, and a z vector for each qubit, and we're taking inner products of those to get our objective function, you know, to relax our objective function. And so this is how we get back to the classical problems that I mentioned in the beginning. So the rounding here, you know, as mentioned before, we want to get to a product state. The rounding here is using a generalization of hyperplane rounding by Briette et al. It's the version they used for their rank-constrained max cut problem. And to kind of lay it out, if we start with a vector solution, as on the previous slide, classically, we just have a single vector per variable, and we're going to project that onto a random vector and normalize to get a plus or minus 1 value. Here, the output should be 3 scalars whose squares sum to 1. And so one way to do this is now we kind of project using a vector that has dimension 3 by 9n, where 9n, is kind of the space where these 3 vectors live in. So here, this is just particular to max cut, but for max cut, it turns out that we can do the rounding in a very simple way where we can just concatenate our 3 vectors and then together round them to a 3-dimensional vector and then normalize it. So we don't really have to treat them as individuals, in doing this rounding. And the reason for that is because the objective function kind of treats these 3 inner products in kind of the same way. But for more general problems, this isn't the case. And that's one of the reasons why it's much harder to approximate more general quantum CSPs. So the rounding algorithms, again, are here we're rounding vectors to scalars. Here we're rounding vectors to collections of scalars to get 3-dimensional vectors. And they have to be normalized. So briefly, I want to mention how this recipe differs for our problem. For our problem, once we've relaxed and we have an objective function value, this is what it looks like. So as part of the input, we're given these vectors that correspond to linear terms. And then we're given this 3 by 3 matrix that corresponds to the quadratic part. And then, the objective function value for each edge is just informed by inner products of these vectors. Here we use kind of a dummy vertex, to keep track of the linear part, just like we do in classical CSPs. But the point is that if we want to approximate this, we have 30 parameters, 15 for the cost and 15 from our relaxation. And so one thing that ends up being really difficult is with classical CSPs, we kind of numerically optimize and we call it a day. There has been more work in using things like interval arithmetic to make those kind of more precise, but still, just like the original Gomez-Williamson result, we approximate the 0.878 and that's good enough. Here, we need to solve integrals to kind of get the right expectations for rounding schemes and stuff. And we have so many parameters that they often have poor convergence, or sampling doesn't work so well. There are kind of irregularities in the space, other issues. And so we can't trust the numerics. And this is one reason why this is much more difficult than the classical case. It's just the sheer number of parameters we're working with. So the way we do this is we actually still are able to do this in a kind of black box fashion by leveraging work of Briette et al. There they show that if you have this kind of setting where your matrix A here is symmetric PSD, then you can actually get a reasonable approximation. And our matrix A isn't symmetric PSD, so we have to do a little bit of work to make it so. And then we can kind of use that as a black box. That's not the end of the story. To actually get a decent relaxation, we need to figure out how to handle linear term. And then we also need a strengthened SDP. We need kind of second moment constraints to get it strong enough to get a decent approximation. So all of these details are in the paper, but really the point of this talk was just to kind of set up these quantum optimization problems. So the main open questions are really, let's apply the classical kind of machinery, to these problems. I mean, what can we say about SDP gaps? And ultimately, we're solving kind of these rank-constrained generalizations of max cuts. Are there any unique games hardness results? For regular rank-constrained max cut by Briette et al., they have unique, they have, for a version of that problem, they have unique games hardness results. And so for these quantum problems, or at least product state approximations of the quantum problems, can we get something similar? There's also, there's kind of a search for a quantum version of the PCP theorem. And although this doesn't directly shed light on that in the setting where people want it to, which is like BQP versus QMA, here we're still kind of saying something about P versus QMA approximations. And so more generally, what we'd want approximation algorithms that are actually quantum, or a slight weakening of this would be approximation algorithms that are maybe classical, but produce descriptions of quantum states as output, kind of like the Anshu et al. Result I mentioned earlier. So I feel like these problems are accessible to those of us who grew up working on classical approximation algorithms. And I think it's a very interesting playground to develop generalizations. And I want to see, it'd be great if we could see more people kind of from approximation algorithms pick this up. Thanks for your attention, and hopefully I'll catch up with you in the actual presentation session.